In the first lesson, we defined the concept of digital system. And in the second lesson, we presented several methods of specification of digital systems. Today, in this third lesson, we will concentrate on electronic systems. First, a previous observation. A real digital system includes input devices, for example, sensors, keyboards, microphones, communication receivers, and so on. It includes output devices, for example, displays, motors, communication transmitters, loudspeakers. It must include input converters to translate the information generated by the input devices into discrete electrical signals, and output converters to translate discrete electrical data into signals that control the output devices. And finally, the kernel of the system, it includes a digital electronic circuit that generates output data in function of the input data. Thus, the complete system looks like this one, with a set of input interfaces, a set of output interfaces, output converters. Here are the input devices, here the output devices. And the kernel of the system is a digital electronic system whose inputs and outputs are discrete electrical signals. This course is about digital electronic system. The inputs and outputs of a digital electronic system are binary encoded data. Two examples of binary encoding are the following. Numbers can be represented according to the binary numeration system. If we want to represent decimal number 12 in binary, it's a 4-bit number, 1100. Another example, 25 in binary is 11001, 16 plus 8 plus 1. Another type of encoding is used for encoding letters, digits, some symbols, or encoding characters. In other words, it's the ASCII code. Now, to build digital electronic circuits, we need digital components. The first point, is how are we going to represent the bits 0 and 1? For that, we define a low voltage, VL, and high voltage, VH, and conventionally state that VL represents bit 0 and VH represents bit 1. In what follows, we will define VL equal to 0 and VH equal to 1 volt. Next point is the transistors, most transistors. Nowadays, most digital circuits are made up of most transistors. Most transistors are very small devices. A large integrated circuit might contain millions of them. They have 3 terminals called source, gate, and drain. And there are 2 types of MOS transistor, depending on the majority carrier. Those types are NMOS and PMOS. In the case of the PMOS type, observe that the little circle has been added to the gate terminal. How can we describe the function of the working of a transistor? We will use for that a very simplified model and consider that transistors are switches controlled by their gate voltage. Switch with the control voltage, actually the voltage on the gate of the transistor. But as we will see, it's not a good switch for any value of V in. Let us make the following experiments. First, in the case of an NMOS transistor, we will consider that the input signal is the left-hand terminal, this one, for example, this one. That is to say the source of the transistor, and the input signal is the right-hand terminal, or here too, and it's the drain of the transistor. Then, first experiment. If the gate voltage is 0 volt, then the output is disconnected from the input. We could say that the corresponding switch is open, and this is true independently of the value of the input voltage. Now, if the gate voltage is 1 volt, as here and here, then the output voltage depends on the input voltage. If the input voltage is 0 volt, then the output voltage is also 0 volt. And the transistor in this case works like a closed switch. But if the input voltage is 1 volt, then the output voltage is not 1 volt. It's greater than 0 volt, but it's smaller than 1 volt. So the conclusion is that this type of transistor, NMOS transistor, is a good switch, a perfect switch for transmitting the low level 0 volt, as was the case here, but is not a very good switch for transmitting high voltage level, 1 volt in our case, as in this second experiment. Now, what about PMOS switch? We make the same kind of experiment with a PMOS device, and we see that if the gate voltage is equal to 1 volt, or generally the high voltage, then the switch is open. If the gate voltage is 0 volt, the low level, then once again the output voltage depends on the value of the input voltage. If the input voltage is 1 volt, then the output is also 1 volt. We see that the PMOS switch works as a closed switch when its gate is at 0 volt and its input voltage at 1 volt. If the gate is 0 volt but the input voltage is 0 volt, the output voltage is not exactly equal to 0 volt. It will be smaller than 1 volt, smaller than the high level voltage, but a bit greater than the low level voltage. So we will say that PMOS is a very good switch for transmitting high level, in our example 1 volt, but a not so good switch for transmitting low level. By connecting several transistors, we can implement small components called logic gates. The simplest one is the inverter. It consists of an NMOS transistor and a PMOS transistor. The PMOS transistor source is connected to the high voltage. Its gate is connected to the input and its drain is connected to the output. The source of the NMOS transistor is connected to the low voltage. Its gate is also connected to the input and its drain is also connected to the output. Assume that the input voltage is 0. Then the NMOS switch is open and the PMOS switch perfectly transmits 1 volt, so that the output voltage is 1 volt when the input voltage is 0 volt. Conversely, if the input voltage is 1 volt, then the PMOS switch is open and the NMOS switch perfectly transmits 0 volt to the output. Conclusion: an inverter inverts the input signal. It transforms 0 volt on the input to 1 volt on the output, and conversely 1 volt on the input to 0 volt on the output, as you can see in this table. And this is the symbol we use for representing an inverter. A second example, with 4 transistors, we can implement a circuit called NAND gate. If V in 1 and V in 2 are equal to 1, then both PMOS switches are open and both NMOS switches are closed, so that the value 0 is transmitted to the output through the 2 NMOS switches. Conversely, if b in 1 or b in 2 or both are equal to 0, then at least one of the two PMOS switches is closed and transmits 1 to the output. At the same time, if one of the two input voltages is equal to 0, at least one of the two NMOS switches will be open. Thus, the result is shown in this table. The output is equal to 0 if and only if both inputs are equal to 1, in which cases the 0 is transmitted to the output through the two NMOS transistors. This component is called NAND 2 gate, 2 because there are two inputs, and this is the corresponding symbol. Now we propose you a quiz. Other components can be defined. We are going to mention some of them. An OR2 gate generates an output 0 if and only if at least one of its inputs is equal to 1. And you see here the symbol. An N3 gate generates an output equal to 0 if and only if its three inputs are equal to 1. An AND2 gate generates a 1 at its output if and only if its two inputs are equal to 1. This is the symbol, and you can check that in fact an AND2 gate can be built connecting an inverter at the output of a NAND 2 gate. Actually, the gate name NAND comes from not AND. Not is means inverter. Other components are the OR2 gate, whose output is equal to 1 if and only one of its inputs is equal to 1. This is the symbol, and you can check that it's equivalent to this small circuit, an OR gate with an inverter at its output. Actually, no means not OR. You can build 3, 4, 5 input components. For example, an AND3 with this symbol is a component whose output is equal to 1 if and only if its three inputs are equal to 1. And it's also equivalent to a NAND 3 followed by an inverter. Another type of component is the buffer. Actually, a buffer is a kind of power amplifier, and its output is equal to its input. A three-state buffer is a control switch. If the control voltage is equal to 1 to the high voltage, more generally, it is like a simple buffer, and the output is equal to the input. But if the control voltage is at the low level, 0 volt, then the output is disconnected from the input, like an open switch. Other components such as multiplexer, decoders, latches, flip-flops, and so on will be defined later on. Now let us give an example of a much larger component, namely a read-only memory. As an example, consider a 12-bit ROM that stores 4 words. Every word has 3 bits, and for that we need 2 address bits. With the address bits x1 and x0, we select one of the 4 stored words. For example, if x1, x0 is equal to 01, that means address 1, then the output Z2, Z1, Z0 will be equal to 1, 1, 1. More generally, if there are n address bits and every word has m bits, then the ROM stores m times 2 to the n bits. The central topic of this course is the synthesis of electronic digital systems, and the problem can be stated as follows. On the one hand, we specify an electronic system. On the other hand, we have a catalog of available components such as logic gates, memories, predefined subsystems, and so on. The objective is to generate an hierarchical description whose final blocks are components belonging to our catalog. In this lesson, we have defined the concept of digital electronic system. We have assumed that all the data to be processed are binary encoded. We have introduced the concept of digital component, and we have defined the main topic of this course, that is the synthesis of digital electronic systems.